Okay, so chapter 2 is about gravitational fields. First point, gravitational field is an example of a field of force. Gravitational field. So example, because of gravity, you can stand on the earth. Okay, so that is a field of force. So let's say this is the earth, and you can stand on it because the earth is having gravity. So that is the basic example. Now let's move on. Gravitational field strength. Gravitational force per unit mass. Per unit mass. Okay, so we learned gravitational field strength last time. Okay, where it is like this. You see the example here. Fg, let's say I call it gravitational force. Gravitational force, Fg, equal to mg. Mg, gravitational force equal to mg. So G is gravitational force over m. So gravitational field strength is actually G. It's actually G. And because of this, then everything should make sense already. Gravitational force, the Fg, divided by the mass. So, of course, on the surface of the Earth, G is 9.81. But this chapter is not just on the surface of the Earth; it go beyond that. So you have to recalculate G sometimes. So depends on where we are talking about. Maybe on Mars or on Jupiter, on the Sun. So it go beyond the surface of the Earth already. Now let's move on. Describing a gravitational field. For an isolated point mass, the gravitational field is spherical in shape with the mass at the center. So this is a point mass. So the gravitational field is inward, it's attracting. Okay, so in sphere shapes, so it's in that way. That is how the gravitational field looks like. Now next point, the gravitational field is described by the field lines. A field line is the path followed by a free unit mass in that gravitational field. So they are trying to say that this arrow means something. This arrow means, let's say this M, this capital M is the Earth. Yeah? This arrow means, let's say if you have a stone somewhere in the sky, so the stone will go down, follow the arrow, go down. So that arrow means something like that. Okay, the direction of the free mass. Okay, the directions of the free mass when it fall down. So it will go this way. So it will go this way. So logically, it's true, So it just fall down. Now, 2.2, Newton's law of gravitations. So gravitational force between 2 point masses is proportional to the product of their masses and inversely proportional to the square of their separations. Okay, so what are they trying to say here is gravitational force is proportional to the product of the masses and then divide by the distance, the square of their separation. So r square. So that is Newton's law of gravitation. They say something like this. And after that, when it is proportional, so we can change it to an equation by using a constant. So the constant will be the capital G here. And we get this formula. So the formula is given here. And the G is mentioned here, gravitational field constant, 6.67 times 10 to the power of negative 11. Okay, so this is given. This value is given. So you just need to substitute into the formula. So M and M are two masses, and R is not the radius. R is the distance between the two objects. So you will get the gravitational force when you use this formula. Okay, gravitational force. So let's say example. Okay, if you have the sun and the earth. So let's say the big circle is the sun. So the sun have mass capital M. The earth have mass small m. Okay, so the distance is from the center of the mass. Okay, this is the R, the distance between the sun and the mass. Okay, so you use this formula, then you will get the gravitational force. So gravitational force is what kind of idea? It's like, imagine that the sun and the earth are just having a fixed distance from each other, and the earth is keeping the distance, and rotating around the sun. Okay, so why it can keep that distance? Because there is a gravitational force that hold it. Okay, so you have to know that gravitational force happens when two objects have masses. So that means they attract. Okay, they attract each other. So the attraction here is not affected by the mediums in between. No matter in between is vacuum or having air, so the attraction is the same value. Okay, so they attract each other. Okay, so now next point, the gravitational force between two masses is independent of the medium separating the mass. So that means no matter there is nothing in between, or there is air in between, or there is liquid in between, or there is a solid in between, let's say there is another planet in between, it doesn't matter, man. The gravitational force is the same value. Okay, and it's always an attractive force. So attractive force, they attract each other. Okay, so now let's just move on. Let's see how we apply this gravitational force in the question. On the next page, we have this. Okay, so this is the questions. Let's go through first. The orbit of the Earth, mass 6.0 times 10 to the power of 24, may be assumed to be a circle of radius 1.5 times 10 to the power of 11 meter with the sun at its center as illustrated in figure 1.1. So you can see the sun and the earth. So they give you the mass of the earth, and the mass of the sun is not given. They give you the radius. So the time taken for one orbit is 3.2 times 10 to the power of 7. Okay, so this is period. This is period. So this is period. So let's write down. This is period. Period T. Time for one oscillation, or time for one round. Okay, so calculate the magnitude of the angular velocity of the Earth about the Sun. Okay, angular velocity. So it seems like this is chapter 1. So it's chapter 1. Okay, angular velocity. So we know angular velocity from the previous chapters. where angular velocity is omega, which is 2 pi over t. 2 pi over t, yeah. So 2 pi because it moved one round. The angle is 2 pi. The t is 1 period. So the period is given 3.2 times 10 to the power of 7. So we will get this value as 1.963 times 10 to the power of negative 7 radian per second. So we round off. Angular velocity. Now, number 2, the magnitude of the centripetal force acting on the Earth. Centripetal force. Okay, so to find centripetal force, it is very normal to think of mr omega square, centripetal force. As we know omega already, which is from the first part, so logically this should come to the mind. So now, okay, so let's make ourselves clear on this m. This m, should we take the mass of the sun or the mass of the earth? So the idea is this m is the mass of the rotating object. So we assume that the earth is rotating around the sun, so the rotating object, the mass is the one that you're supposed to put here. So you put the mass of the earth here, so which is given 6.0 times 10 to the power of 24. So we put inside. The radius is given 1.5 times 10 to the power of 11, and the omega is 1.963 times 10 to the power of negative 7 square. Okay, so by pressing calculator, we will get the answer as 3.46978 times 10 to the power of 22. So if we round off this to 3 significant figure, then it's going to be 3.47 times 10 to the power of 22. Okay, so that is like chapter 1 thingy. So we just move on to the next page.